Hi everyone, so I have a fascinating problem for you today and it's a little bit rigorous but I'm sure you'll enjoy it a lot. So today we're going to discuss about polynomials and the Euclid's division lemma. So let's just get started. This is the problem B5 from the Putnam exam in 2007 and in this video we're going to be looking at polynomials and the floor function. We also have a very important result, a lemma essentially that you can use in your repertoire. Then we have Euclid's division lemma, which I'm going to use to prove the before said lemma. Then we have certain book sessions for college mathematics, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what does the question say? So it looks quite big, but it's actually asking you to prove a very interesting result, right? So they're saying that let k be a positive integer and then prove that there exists polynomials p0, p1, p2, p3 all the way up till pk minus 1 such that they satisfy the given equation. So basically we have this given equation, it includes the floor function of certain terms and we then essentially need to prove that the polynomials exist, right? We need to check for the existence of such polynomials. Essentially we need to prove that such polynomials exist, right? Okay, great. So this is quite rigid. So it's I think it's better to maybe take it one step at a time, right? And take certain simple cases. Essentially what the question is asking you to do is it's asking you to prove a lemma, right? This is a very generalized lemma. You have n, you have k, k minus 1 polynomials. So all, it's a very generalized statement. So whenever you have certain generalization like this in n, k or anything, we tend to first look at certain simpler cases, right? And then maybe generalize it using certain techniques that we can use, right? So let's maybe just consider certain simple cases. So maybe let's consider k is equal to 3. Right? And maybe we'll also see k is equal to 2 and just see how these simple small terms work out. So if I have k is equal to 3, then I will have the polynomials p0x, p1x and p2x, right? Because it goes to k minus 1. Okay. And these polynomials, I need to prove that they exist such that they satisfy this equation, right? So n by 3, floor of n by 3 cubed is basically p0n, right? Plus p1n times the floor of n by k plus p2n times the floor of n by k whole squared, right? So I need to basically prove that for this k is equal to 3. This is a very special small case that I just need to prove that p0, p1 and p2 exist. And if they do exist, that means this result is true for k is equal to 3. Okay. So how do we proceed with this? Well, I think it's a good thing to let's analyze what this floor of n by 3 looks like. And we'll take different values of n. So maybe you plug in n is equal to 6, right? So you'll get floor of 6 by 3, which is obviously 2, right? Then maybe you take another number, you take 7 by 3. The floor of this will be 2 obviously, but I can also write that as 7 minus 1 divided by 3. Same result, right? 2. I also have 8 by 3. I can write this as 8 minus 2 by 3. Same result will be 2. Right. If I have the floor of 9 by 3, that will essentially be 9 by 3, which is 3. If I have the floor of 10 by 3, this will be 10 minus 1 by 3, which is 3. And that's just, so on and so forth. You can plug in certain other values as well. So if you actually notice, I'm either subtracting 0, I'm either subtracting 1, or I'm subtracting 2. So either I'm subtracting nothing from the number, or I'm subtracting 1, or I'm subtracting 2. And this process will keep on repeating. So for example, if you have floor of 11 by 3, this will be what? 11 minus 2 by 3, which is 3. And again, 12 by 3, I'll subtract nothing because it's just a whole number 4. So basically, n by 3 is taking the values n by 3, n minus 1 by 3, or n minus 2 by 3, which is very fascinating, right? N by 3 can only be one of these 3 possibilities, right? It's very simple. Here it is basically n by 3, Here it is n minus 1 by 3, n minus 2 by 3, again n by 3, n minus 1 by 3, n minus 2 by 3, and the pattern just keeps on repeating. So n by 3 really is just one of these three things, right? So another way to write this is floor of n by 3 minus n by 3 is equal to 0, or floor of n by 3 minus n minus 1 by 3 is equal to 0, right? Or floor of n by 3 minus n minus 2 by 3 is equal to 0. So it could be one of these three things. We don't know what that is. It could be any one of these three things depending upon the value of n. Okay, so that necessarily implies that the floor of n by 3 minus n by 3 times the floor of n by 3 minus n minus 1 by 3 times the floor of n by 3 minus n minus 2 by 3, this entire thing needs to be 0. Why? Because either this will be 0, or this will be 0, or this will be 0. One of these three quantities has to be 0. And if one of them is 0, you multiply them by the other two will also get 0. Because 0 multiplied by anything is 0. So just another way to write it, right? And this is very fascinating, because now if I just take maybe the floor of n by 3 as t, I'll get a polynomial equation in t. So t minus n by 3, t minus n minus 1 by 3 and t minus n minus 2 by 3 is equal to 0. And when I just expand this, I'll get a polynomial equation, and it will be like t cubed is equal to something, right? I'll have t. So basically what I'm trying to say is that I'll have t cubed, right? I'll have t cubed, and the coefficient of t cubed will be obviously 1, right? So I'll get t cubed is equal to a bunch of expressions, right? So I'll get t squared times something, right? I'll get t times something. You can expand this out, whatever it will be. I'm just giving the idea. And then there'll be like a constant term. A constant, I mean in just in n. It's not going to be multiplied by any t. So t raised to power 0 times something. And this something will be a polynomial in n, right? All of these somethings, all of these gaps that I'm leaving over here will be a polynomial in n. So you see, this was what? This was, I believe, p2x or p2n. This was p1n, and this was p0n, right? So there do exist certain polynomials, or there will always exist this polynomial, right? Because when you just expand this, this is a very important equation. Let me just label this as number 1. If you just expand this equation number 1, you'll get t cubed. You'll get some terms with t squared. You'll get some terms with t. You'll get some terms with t raised to power 0. No power of t, right? And those terms, whatever the power of t is, it will be multiplied by a polynomial in n. So therefore p0 exists, p1 exists, and p2 also exists, which is what we had to prove, right? So for this case, k is equal to 3, we prove that p0, p1 and p2 exist, which is awesome, right? Because now that we've seen it for k is equal to 3, can it work for any k? So for k is equal to 3, it works, right? Now my question is, what if we had a generalized k, which is what the question is asking us to prove, right? And which is the main crux of the problem, right? So if you actually see, floor of n by 3 was n by 3, n minus 1 by 3, or n minus 2 by 3. By the same observation, or by the same analogy, if I were to generalize floor of n by k, how would it look like? It would be n by k, or n minus 1 by k, n minus 2 by k, and this would go all the way up to n minus k minus 1 by k, right? Here this is the generalization for k is equal to 3, and this is obviously the generalization for any k, and this is just kind of like observational result. I think I'm not proving this formally right now. I will prove it in the later section of the video, but right now you just kind of need to understand the floor of n by k will either take one of these values. So it can basically either be this or this or this, all the way up till this. It will take one of these values. So basically, kind of using the same idea, floor of n by k minus n by k is equal to 0. Floor of n by k minus n minus 1 by k is equal to 0. And you can just go on and on and on and on until you get the floor of n by k minus n minus k minus 1 by k. This entire thing is equal to 0. So one of these things is 0. We don't know which of them is 0. Either this is 0 or this is 0 or this is 0 or this is 0. One of these will happen. For sure one of these will happen. And because of the certainty that one of these will happen, I can basically write this as floor of n by k minus n by k times the floor of n by k times minus n minus 1 by k. And not just using the same idea as we've done before, and this you multiply all the way up to floor of n by k minus n minus k minus 1 by k. Basically the same thing that we had done before, and this will obviously be 0. And the same thing that we have done 0, one of them has to be 0. Let's multiply it out and the entire product will be 0. Right? Now what? Now you take again kind of the similar ideology, exact, it's purely analogous. You take it as t. So you will get t minus n by k. Right? You'll get t minus n minus 1 by k. Right? And this will obviously go on and on, right? This will go on and on till t minus n minus k minus 1 by k. Right? And this will obviously be 0. So you will get a polynomial in t. Right? Otherwise, I should put it like this. I'll get something like t raised per k is equal to some certain quantities, right? Equal to certain quantities. You will get basically t raised power 0 times a certain polynomial. T raised power 0 times a certain polynomial, right? Plus t raised power 1 times a certain polynomial, right? Plus t raised power 2 times a certain polynomial. And this will go on and on. Basically, like we had above, right? Like I was doing above, like I was taking this t over here as well. Right, in this equation number 1, I got P0, P1 and P2 because K was 3. You get K minus 1 polynomials. Right, here K is K, basically the generalized case again we'll get K minus 1 polynomials. So we'll get P0, we'll get P1, we'll get P2, we'll get all the way up till Pk minus 1, which is what we have to prove. And we have proven that in a way. Right, because we have essentially stated that this T, which was floor of n by k, raised to the power k is equal to this polynomial, and that is what we had to prove, right? Let me just go back to the question. There we go. We just need to prove the existence of these polynomials. We don't have to necessarily find them. We just need to prove that they exist. And do they exist? Yes, they do. Of course they do, right? Because t was n by k. This you will get t raised to power k. So basically, floor of n by k raised to power k will be a certain polynomial combination of this n by k. Right, so you'll get these polynomials P0, P1, P2 and so on and so forth, and they will be of the form obviously P0 n plus P1 n times floor of n by k, right, plus P2 n floor of n by k whole square and so on and so forth. Right, I had just taken this floor of n by k to be t. So will these polynomials exist? Yes, they will. And they will exist as a consequence of you multiplying out these terms. Take floor of n by k as t, just to simplify the calculation a little bit, just to simplify your understanding a little bit, and then just visualize that when this entire thing opens up, when you multiply out all of these terms, you will get a polynomial equation, right? In better words, I should say that there will exist these certain polynomials that will be filling these blank gaps. Over here, this will be a polynomial, this will be a polynomial, this will be a polynomial, and what will be those polynomials? This will be what? P0x, this will be P1x, this will be P2x and so on and so forth, right? The polynomials will exist. And it will go all the way up till P sub k minus 1x. So do these polynomials exist? Yes, they do. And that is what we have to prove. But that being said, I made a little bit of an ad hoc assumption. And that was that, where did it go? This result, equation number 2. I just kind of used my observation over it, which is fine, but there actually does exist a formal proof for that, and that's a very interesting lemma, right? So the lemma, right? So the problem is basically over, but I'm just trying to prove that the lemma, the result that we had formulated above. So the lemma states that for fixed k, floor of n by k will be from the set n by k, n minus 1 by k, n minus 2 by k, all the way up till n minus k minus 1 by k. Right, so it will be basically one of these values, and this is essentially what I had said above as well, but basically now I'm going to try and prove this formally using a little bit of algebra. Earlier it was just observation, right? Now I'm going to try and prove it like a little bit algebraically. So basically what happens, so if I prove this lemma, then this is true, right? If I prove this lemma, basically rather this is true, and if this is true, equation number 2 is true, then obviously this is true, and if this is true, then the polynomials P0, P1 exist and the question is proved. So basically, if you just formally prove this lemma, our question is done, right? Okay, how do we prove this? Well, we use the good old Euclid's division lemma, right? Any number n can be written as kq plus r, and there's a condition on r, the remainder, that it needs to be greater than or equal to 0 and needs to be less than k minus 1, right? You all know that. Now if I try to maybe formulate n by k somehow, because I wanted to find out the floor of n by k, so let's just see what n by k is. So I just divide both sides by k, right? So I'll get q plus r by k, and after this point I'll just take the floor on both sides. Now since q is an integer, it just comes out, right? Q is an integer, it comes out, plus the floor of r by k. Now you see, r is something which is between 0 and 1, right, in a way. So the floor of this will obviously be 0, because k is also a positive integer, so floor of this will obviously be 0, right? So essentially the floor of n by k is only going to be q. The floor of n by k is going to be q, but what is q? If I go back over here, n is equal to kq plus r, so can I write q is equal to n minus r by q? N minus r by k? I'll just rearrange the terms to make q the subject, right? So q is basically n minus r by k. So floor of n by k is n minus r by k, and this is true for all r's from 0 to k minus 1, right? From 0 to k minus 1, because r is from 0 to k minus 1, right? That was the kind of constraint that we had to apply this division lemma, right? So r needs to be from 0 to k minus 1. So this formula that I've written over here, it works, it runs effectively from all r's from 0 to k minus 1. So basically when you just start plugging value of r 0, 1, 2, 3 all the way up till k minus 1, you will get that the floor of n by k will be either n minus 0 by k, n by k, n minus 1 by k, n minus 2 by k, all the way up till n minus k minus 1 divided by k. So that is what the lemma was, right? I had to essentially prove that. So I proved this lemma. That means that what I had done above, so where did it go? Yes, this lemma is true. That essentially means that what this product is true, and that essentially means that there will exist this polynomials p0, p1, p2 all the way up to pk minus 1, and therefore the polynomials do exist, and that's it. We've proven the question. So yeah, it was a little bit rigorous, also very fascinating application of polynomials and the floor function, which is really beautiful. So I hope you enjoyed that. Okay, so moving on to some book sessions for college mathematics: Introduction to Real Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galian, Topics in Algebra by Herstein, Abstract Algebra by Dumit and Foote, and of course Linear Algebra done right by Axler. Cool. So at the end we have a similar but challenging problem, and we need to determine the number of real positive a which is less than or equal to 2021, so that there exists polynomials with integer coefficients where this ratio or this fraction is a natural number, right? So we need to find out the number of real and positive a so that they are less than or equal to 21, such that if I kind of figure out the value of this fraction, I will always get a natural number. Let's say that is k, right? And this obviously works for all x comma y that are natural numbers. So maybe try this out, and if you're able to solve it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians, and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.